Hello, this is Math 2134 coming to you from the College of DuPage, and the title of this lecture is One-Sided Limits and Continuity. Recall previously we said that the limit of this blue function does not exist when x equals 0 because when we approach x, approaching 0 from the right, and we're riding along the curve, we get closer and closer to 1. But when we approach 0 from the left with x, and we ride along the curve, we're getting closer and closer to -1. So the limit from the left and the limit from the right do not equal one another. We now have notation for that and a definition. So the function f has a right-hand limit L as x approaches a from the right, and it's written the limit as x tends to a, and then there's a little exponent there that is like a plus sign. F of x is equal to L if the values of f of x can be made as close to L as we please by taking x sufficiently close to but not equal to a and to the right of a. And similarly, the function f has a left-hand limit M as x approaches from the left, written the limit as x tends to a, and then again it looks like a little exponent but is a minus. F of x is equal to m if the values of f of x can be made as close to m as we please by taking x sufficiently close to but not equal to a and to the left of a. And as we said before, I think we've quoted this before, but the limit from the limit as x tends to a of f of x equals L if and only if the right-hand limit, the limit as x tends to a from the right, is equal to the limit as x tends to a from the left, and they both equal the same L. So here's a problem. You have an f of x that's defined this way, piecewise, and a g of x that's defined this way. So what we're supposed to do is show that the limit as x tends to 0 of f of x exists by looking at what we have here. And then in part B, we're to show that the limit as x tends to 0 of g of x does not exist. You know what to do. Let's see how you did. Well, the point where there's any question is at 0, and so if you're less than or equal to 0, the limit as x tends to 0 from the left of f of x is equal to the limit, and the definition if you're less than or equal to 0 is minus x, so that is 0. Similarly, if x is bigger than 0, this is the definition, but then the limit as x tends to 0 of f of x is equal to x tending to 0 from the right, and that's the square root of x. You can just plug it in and you get 0. So the limit from the left and the limit from the right both equal 0. That means that the limit exists and equal to 0. Now this is the function actually very similar to what we talked about before. I guess this is just flat though. So the limit from the right is equal to 1. The limit from the left is equal to -1. So by that theorem we quoted, the limit does not exist. Now, continuous functions will play an important role throughout most of our study of calculus. Loosely speaking, a function is continuous at a point if the graph of the function at that point does not have holes, gaps, jumps, or breaks. So for example, here we're being continuous, but we come here and there is a gap that happens at A. So there's a hole, that's a gap. Here there is a gap and a little bit of a jump. And here there is definitely a jump. And here there's a case where the function just breaks. Now, another way that students often think about this is a function is continuous if I can draw it without lifting my pencil. So if I'm going along here to cross this point A, I would have to lift my pencil to go to the other side. Here I would have to lift my pencil and dot to this. Here I would have to lift my pencil to get up to this one and continue. And here I would have to lift my pencil to start on the other side. Now that is all kind of loosely speaking, but here's a real definition of a continuous function at a number. A continuous function, f is continuous at a number x equal a if the following three conditions are satisfied. F of a is defined. The limit as x tends to a, f of x exists, and the limit as x tends to a of f of x is equal to f of a. In other words, I can graph it without lifting my pencil. If f is not continuous at x equal a, then we call it discontinuous at x equal a. And also if f of x is continuous on an interval at every number in the interval, then it's called continuous on the interval. So for example, going from here up to almost to a, that would be continuous because I can trace it that way. Here's another example. Actually, this is 5 examples, and we're to determine the values of x for which each function is continuous. Recall that there is a convention that we, unless stated otherwise, assume the function is continuous for all real values of x except where it is undefined. So you have 5 examples here. You know what to do. Let's see how you did. Okay, here this is defined for all real values of x, so this is continuous everywhere. B, this is not defined and is not continuous at x equal 2. And we can see that, well, we can see the first problem from here. This one is not continuous at x equal 2 because there is a hole there. Now, we've done this problem before. If we factor the numerator and denominator, we can factor and cancel the x minus 2. So this function and this function look the same except at x equal 2, but this one has a hole. For this one, there is one of those jump discontinuities. We're going along here, we hit the hole, we have to pick it up and go down here, so this is discontinuous. This one, wow, I think we pretty much talked about this one before. This one, it jumps from here to here. And the last one is constant going to here, but then it goes 1 over x. So those are the 3 different kinds, and they are described here. And so let's see. So this is going to be all real numbers except 2. This one is all real numbers except 2. This one is discontinuous at x equal to 0, and this one is discontinuous at x equals 0, and it's summarized over here. Now, continuous functions are nice. The constant function certainly is continuous. That's a flat line. The identity function y equals f of x equal x is also continuous everywhere. And if you raise a continuous function to a power, it's still continuous. If you add or subtract 2 continuous functions, they're still continuous. And if you take the product of 2 continuous functions, it's still continuous. And in fact, you can divide continuous functions, provided that you stay away from points where the denominator is equal to 0. So that means a polynomial, you know what this looks like, is always going to be continuous at every value of x. And a rational function is also going to be continuous at every value of x, except when the denominator is equal to 0. So here's an example where to find the values of x for which each function is continuous. And so we have a, b, and c. We have 3 functions, a polynomial, and 2 rational functions. You know what to do. Let's see how you did. This is a polynomial, so it's continuous everywhere. This one is also going to be continuous everywhere because the denominator is never 0. So that's continuous for all real numbers as well. Here, you can factor the denominator, and the denominator would factor this way. And that means you have to stay away from 2 and 1. But everywhere else it is continuous. Here's an applied example dealing with learning curves. People are interested in how fast people learn. And generally what happens is you start out making a lot of improvement, then you kind of slow down as you reach some kind of a limit. In this case, what happens is the person starts out fast, but then they start bogging down. But then there's some kind of a breakthrough where they really understand something, and they jump up to this, and then they start learning again. My point is that this is a real-life example of a discontinuous function at that point where the breakthrough happens. We have another concept dealing with what is called the intermediate value theorem. You see, when we think about the train moving along a straight stretch of check, it can't vanish and appear somewhere else. It has to go through all the intermediate points. And that's kind of what the intermediate value theorem is about. And here's a statement of the intermediate value theorem. So, if f is a continuous function on a closed interval ab, and m is any number between f of a and f of b, then there is at least one number. This is an existence proof. It doesn't tell you what that number is, c in ab, such that f of c is equal to m. And what that's really saying is if I start here and I get over here, I have to cross any number in between, at least once. I could do it multiple times. This just says there's at least one such number. Now, the next theorem is an immediate consequence of that. You see, here we're using the number in between f of a and f of b is going to be 0. So, the theorem is entitled The Existence of Zeros of a Continuous Function. If f is a continuous function on a closed interval ab, and if f of a and f of b have opposite signs, then there's at least one solution of f of x equal to 0 in the interval. And you can see that if it was not continuous, you could jump and not have a 0 in between. So the continuity is certainly crucial for this theorem to be true. So here we got f of x is equal to this. You're supposed to show that it's continuous, and answer B based on the directions. You know what to do. Let's see how you did. Okay, well, it's a polynomial of degree 3, so therefore it is continuous. That means it satisfies the if part of the intermediate value theorem. And it is negative when you're at -1, and it's positive when you're at 3. That means you have to cross. There's at least one point between those two, such that f of c is equal to 0. Now, this technique actually is used to solve equations. This is what many calculators do. So if y equals f of x equal x cubed plus x minus 1, that's a polynomial, it's continuous, but f of 0 is equal to -1 and f of 1 is equal to 1. Therefore, we know that somewhere in 0, 1, there is a root. But then we pick the midpoint, that's why it's called the bisection technique, and we look at the sign of the midpoint, and then we can determine where the root is going to be by the sign, S-I-G-N, of the midpoint. And so here you can see we get closer and closer to finding out that value of the root, and this can be done to any level of accuracy. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. God bless you all.